Hi, I'm sorry to interrupt. I don't know if anyone can hear me, but Adam, we can't hear you.
How about now? Can you hear me now?
Perf Perfect. Yes, thank
Yes.
you.
Cool. Well, thank you for the heads up. So I'm not sure if I should do a quick Zoom audience recap, but let me go back 2 slides real quick so I can recap. Basic picture. We have simultaneous harms of late diagnosis and over screening. We want to both to solve that. We understand who's going to get cancer and do something about it. And that's kind of the chunk of the talk. We want to motivate how we can get much better cancer risk models. And this is where you said that you couldn't hear, so now we're back at the synchronized time. Uh, this is not a new question. There's a lot of cancer risk models out there today. The NCCN criteria for who gets MRI is based off a model just like this. Look at like age, detailed family history, maybe breast density, which is derived from the image. So they're already looking at imaging in one way, and then you predict who's going to get cancer. The trouble with this approach, despite being the foundation where we are now, is it's just not very predictive. So if you look at, this is experiment on MGH data, who's flagged high risk by current screening guidelines, less than a quarter of people are going to get cancer will be high risk by the time they're diagnosed. And yet the vast majority of people who get told to get an MRI, more than 95%, won't get cancer within the observation period. There's a lot of room for better efficiency here. And now kind of going back to kind of like where this fits within this general vision, a very simple thing. We're using less than a kilobyte. What if we use more? How can we scale this to get to much more predictive power? So it's a build slide. Okay, so I in my PhD, I did a lot of this work. There's a litany of citations on the other side, but the broad scheme is that any place, including here, you have access to so much patient data. You have patients, the full image. Now we're looking at the megabyte regime, so looking at something quite a bit richer in its full pixel glory. And we know who got cancer in the future. And now our task is to let's learn this directly and how much better can we do to understand cancer risk. Now I'm gonna do a quick aside because if you have the images but you don't understand the outcomes, I've had to solve this every place I've gone so far, including at MGH and now at UCSF, is how do you even get those outcomes? So this is a tiny aside. The short answer is if you use LLMs and you fine tune them with like 100 samples, it's totally fine. You can do this for like less than $5. It's to solve a problem, and if people are interested, we can share the fine-tuned models. Everything is open. This is very easy to do now. Okay, so everybody should be able to get, if you have the images, you also have the outcomes. Now, the first model we built in the space, or one of them, is something called Mirai. I'm gonna tell you a little bit about the results, and then we'll talk more how to make it better method-wise. So Mirai is an image-based risk model. We have the 4 standard views of the mammogram, so like, left, right, CC, MLO. And from there, we're predicting not only cancer within a year, which is basically detection, but within 2, within 3, within 4, within 5 years. Now, there's a lot of technical details that are required to make this work. But I'm just going to zoom forward to the results because really what matters about it isn't the kind of raw methods of 2019 when I built this, but the validation post. So the blue bar I'm showing you here is the Tara-QSIC. That was the kind of prior state of the arts, like many pages of questionnaires, super detailed family history, and breast density. So it has more information than the image-only model. And looking at just the image with like tiny old GPUs back in the day, you can get quite a bit better. So that green bar there is Mirai, that's 76. Now, if it was one hospital, maybe it's a fluke, who knows? So I spent a lot of time flying around, cold emailing hospitals. And in the original JCO publication, we showed that you get the same number or actually better in all the held out hospitals was out of the box. Since then, the slide's a little bit outdated, but we've had 66 hospitals across 30 countries test the model. Things are kind of behaving as expected. And this is not a fluke. This is not a breast cancer specific story. We have a very similar model in lung cancer called Cybele. And the blue green bar thing is like same kind of story. The blue bar here is not breast cancer family history, but it's smoking history, number of pack years, and age. That's the Pilco twin itself model. Looking at just a single LDCT, you can do better. And similarly, it's not just that it works on the original data set, which here was NList, but it generalizes out of the box on the modification to held down institutions, including CGMH in Taiwan and MGH in the US. Okay, so I've hopefully convinced you that if you just look at the image and you model this well, you can get much better understanding of what is the risk phenomenon, right? The numbers get better, and it's not a fluke, it's a robust finding, it generalizes, it's not like just in one population. Now, if you're an astute observer, you'd be like, the ACs get better, so what, who cares? Which is a fair question and one I encourage. And we're running multiple prospective trials in this setting. So I'm going to briefly tell you about these ongoing studies. I'm happy to kind of go into more depth about what we're doing there. But then we'll talk about how to make the models better. Okay, so one ongoing study, we've been running that for a couple years. It started at UMass, now we're expanding it to 3 additional sites, is selecting patients for high-risk MRI. So in the very motivation, I told you, if only we knew who might get bad cancer soon, might have the hope to preempt it by giving this person MRI that can catch cancers at a much smaller stage now, with the overall goal to reduce the rate of advanced cancer. So we're already running a trial of that kind now across 4 sites, where if someone's very high risk by MIRI, we're inviting them to MRI. People under current standard of care are already getting invited. We're doing a comparison between our high-risk screening cohort versus normal. That's an ongoing study. Another ongoing study, which is now running in SFGH that relies on like a real-time integration of the model, is just aimed at reducing the harms of the screening workflow. So what I mean by that is right now the normal workflow mammography, if someone comes in, get their mammogram, and at some other point in time later, it'll get batch read of a bunch of other screening mammograms. And so if something's suspicious, someone has to come back. At UCSF, it's like on average, like 1 to 8 weeks later to get the next workup, and then someone will look at that, and maybe a bit later they'll get their biopsy. And given that we can get the risk score in real time, what if we can invite people a fraction of the volume to get something worked up immediately because we know it's before they leave the room? So this is a very, very simple workflow thing. It's been ongoing. We're halfway through enrollments now. We expect that within our high-risk cohort, roughly half of all the cancer that will be found will be in that bucket. And our patient enrollment rate so far is 100%, and patients are giving us positive feedback, and we'll read out results some point later in the summer. And so these 2 things are ongoing. And one thing that is foreshadowing a later part of the talk is I knew this by the time we were starting the trial, but I was going through regulatory approval 3 out of like 17, is that by the time the trial was halfway done, we'd have a better model. And this is already true. This is an unreleased model we'll probably write up sometime this summer, where given a very similar approach, just like new training techniques, we're getting 5 points better AC than MIRI on the detection style workflows, and also much better on the long-term risk workflow. And on the simulations for high-risk screening and this workflow stuff, it's already better. Which kind of shows a challenge, like at its core, can we do better than traditional approaches? Yes, there's more data to be had. But the pace at which we can make these things better is not really compatible with our evidence generation tools. And to foreshadow that, like, we're not done, right? Like everything I showed you here is in this megabyte regime. The whole point, like this motivating slide, is that we don't live in the megabyte regime. Like cancers are the most high stakes scenarios. We have gigabytes of data per person. And so there remains this kind of open challenge. Well, how do we actually model the full context? Because there's so much more we can do in prediction. There's just one mammogram. There's so much more that we have. Like sequential mammo, we have TOMO, we have PATH, etc. So this brings me to some ongoing work trying to tackle the fundamental challenges and making this type of prediction feasible. That's going to get us the next 5 to 10 points above where we are now. It looks like just a single mammogram. This is the focus of a recent paper that's on arXiv as of a couple of weeks ago called Atlas. Now, but before I dive into this method stuff, I want to take a quick moment for questions, because we're about to do a phase shift in style. And all right, rock solid confidence, everybody. Yes.
Cool stuff so far. The breast cancer, do you kind of do some types? And
Yeah, in that paper we didn't, but there's really great evidence that we can now. So the next, by the time MIRI 1.5 comes out, it will. That one it didn't because data infrastructure and it was like a different time, but it will. Subtyping is hard. It's not like we don't have like 95 AUC saying this is going to be like luminal A versus luminal B. Like that's pretty tricky. But can you tell triple negative from not? Like there is predictive power there. How it changes your workflow is not super clear because like we have multiple kinds of interventions, right? But like the most common one that we're interested in is screening. And like if I'm going to give you an MRI, it doesn't really matter if it's going to be like triple negative or not. I mean, like I don't know well enough to make that distinction. I just want to be able to catch more. It will be helpful. So we're trying to build that capacity, but it's not the bottleneck in our current clinical workflow or clinical hypotheses right now, at least. Yes.
so you said the original model was just built for diagnostics, but then when you applied it to like risk assessment, did you have to change the model?
So I skipped this detail. I'll kind of go back. The models actually was originally built for risk. And there's multiple innovations to make this work. But like one of them that I didn't talk about, but I think is probably useful to talk about, is the basic formulation of how you predict risk over time. So we consider time to kind of have discrete bins, like because people show up on an annual kind of basis. And so like what is the cancer risk at year 5? It's really like your 4-year cancer risk plus whatever's marginal hazard on top. And what is the risk at year 4? It's a 3-year risk with something marginal on top. And so we have a kind of cumulative risk layer built into the model, and you maximize the likelihood of the true observations. And so this actually was trained mostly for risk. It just happens that it's actually also a reasonable detector, because the 1-year risk is functionally a diagnosis. And there's a lot of interesting nuances here. Like the reason why the numbers go up, like usually when you show validation plots, numbers go down or they go flat. These go up. And the reason is because you're never predicting risk of cancer, you're predicting risk of diagnosis. And when something is diagnosed depends on the health system and when people show up. And so in places where we have less resources, where screening is less frequent and things are generally caught later, what is a 2-year cancer is not the same as a 2-year cancer here. So the numbers actually go up when screening is less frequent. So in the annual screening, it's kind of around kind of 76 number. When you go to biannual triangle, like the things go up, which is an interesting nuance. Interesting to me, at least. Yes.
Is the model fine-tuned for the other hospitals or completely?
0 shot. Like it's just trained at MGH, everything at like no like exact weights applied everywhere else. Out of the box, no speaking. Yeah.
And then from like the end user perspective, are the radiologists like seeing the risk score? Are they also are they seeing markings on the areas of concern?
Just so like that all depends on the workflow. So like the MRI trial, the actual integration is like someone's high risk and our CRC gets an email notification. So they know if they reach out to this patient. In the workflow thing is the same thing. Like we get their risk score and like that pushes a notification to RedCap to do the thing, because we're not trying to change the way the person reads. Because one, like how would you read it differently if you know the 5-year risk? Like that's more like, then you're looking for like a cat thing. And even then, the real problem is that you actually have too much to read, not you wanted to look at more stuff. So I'm skeptical of that being the right mode of intervention to make people less pained, you know? So we have things in mind there, but it's not in this work.
So I will say, like, I'm a breast radiologist, and our current workflow, we use the Tech-Cruzic model, and that gives, you know, the risk. And I see that when I'm reading the screening mammogram. So inherently there's some sort of bias from seeing that number, that if someone is like very low risk, I might be, and we see it amongst our colleagues and myself, that if someone is very low risk, I might be less likely to call something back versus if someone is very high risk. So it's interesting to see at what time point that information is provided.
Yeah, I think, I mean, the Tech-Cruzic is, I mean, it's not nothing, but it's like barely better than age, like very barely. And so like if I was designing a workflow, I'll probably have that blind until the end, because like you can condition on it, but practically it's not all that meaningful. Even like density by itself, we have a paper upcoming that brings together like 1 million mammograms across some number of countries. Density is a predictor of risk. Is like, is it statistically significant? Is it real? Yes. Is it human significance, as in like high relative hazard? No. Yeah. But I do think there's stuff that's cool in the workflow side that's more around report generation I can talk about at the end. Okay, so that's all like models of the past. Let's talk about how we build the models of the future, right? Because I don't want to do just a single mammogram, which is already quite big. I want to be able to do multimodal longitudinal over time. And that requires like fundamental scaling. And to give a quick preliminary note of like, why is this hard? We're going to move to transformer land. The normal way we think about how to get very rich models is we're going to take our image or volume or whatever, we're going to break them into little unit tiles we're going to call tokens. And even for a single CT at full res, you might get something like 1.6 million tokens. And the most common way we model stuff nowadays is like with vision transformers, where you're going to allow each patch or each token to talk to all the other tokens. Now, the benefit of that, it means that if there's a pattern that lives across 2 tokens that are far away, let's say across 2 CTs or 3 TCs, the path length is just 1, right? So you can get very efficient long-range communication. The trouble is that because you're comparing everything to everything, if there's n tokens, it's O of n squared, right? So like if the image is 10 times bigger, it's going to require 100x more compute. And compared to ImageNet, we're actually 62,000 times bigger for just a single CT. And so this is 3.9 billion times more expensive. And that's outlandish. Like that doesn't work. And so you need a fundamentally new building block to kind of get you something like O of 1 scaling, something that's very efficient in propagating long-range patterns, but does not have this crazy scaling pattern. So that's the goal. And that's what we're tackling with Atlas, the new architecture paper. That is my dog, the best of dogs, but that's not the point. Where we're going to first patchify it in the same kind of framework. And the key of Atlas is a new way to do long-range communication that we call multi-scale attention. Right? And the thing we're trying to get to is we want to do 2 things. So we want to be more efficient. So here I'm just showing you for a 2D image, like just for reference, a mammogram is actually like closer to 4K by 4K. As we scale the input resolution, even all the hardware optimizations like flash attention, like we want to stay very low here while getting a big accuracy boost over things that are comparable speed. So compared to a vision transformer at the scale, we're already more than 7x faster. And as we get to our actual scale, which is like longitudinal scans, this gap keeps growing. And so given this, we want to be, well, how much better can we get than like MAMA, which is a non-attention-based, taste-based model? Okay, so how does this work? There's two key ideas. One key idea is within each multi-scale block, how do you represent our image? And we do something here that's very simple. It's an old school idea. We're going to do multi-scale representation. So we have our tokens. And within the block, we're going to maintain a log n number of tokens. Right? So we're going to have like a pooling function that might take a patch of 2 by 2. We're going to run this over and over again until we only have one window left. Right? So if the image is big enough, we'll have 3 scales. If the image is smaller, it might be 2 scales. If it's really small, it'll be just 1 scale, and then it's like a transformer. Right? So you have multi-scale representations. Right now, it's not faster yet, right? Like at this point, it's just more expensive. You're doing more stuff. The key is how did scales talk to each other? So there's 2 mechanisms that are happening at the same time here. One mechanism is using cross-attention. So you're doing windowed self-attention. So in each scale, there's 2 functions that are happening. You have cross-scale communication and then windowed self-attention. And we're basically propagating information from the coarsest grain feature all the way down to all the features before it. And you're also doing the reverse direction. So you have this kind of bidirectional communication where if you're within one window, you get to look at a coarser version of all the things that are far away. And as it gets further, it gets coarser. And if you're in the window, you also get communication for the finer grain kind of children nodes that you have. And I'm just going to pause there for a second. What that means is, this is not in great detail on the slide, but you get O of n log n computation and O of log n communication. People follow me? I'm showing this as a very pictorial advantage because there's going to be a lot more stuff. That's kind of one key idea. This gives you the multi-scale attention block. The other idea, if you have a block, that's one thing. But then the question is, how do you compose them? How do you get to a full architecture? Right? Because I showed you here that like there's a pacification thing, and then you have to like, there's a macro architecture that gives you a full model. And practically what we find is that this multi-scale function is also a way to downsample the signal. So what I mean by that is in the early blocks, you maintain all the scales. And as you go down each block, you drop a scale each time. And there's going to be log n number of those changes based on input volume. And putting it all together is the full, one direction, the full Atlas model. Okay, so now just kind of diving into the results. These are all kind of, if you remember the original scaling plots, at 1K regime, you can barely see the speed differences. At that point, we're either much faster or much better than any comparable baseline. And this gap just gets bigger as resolution gets bigger. And now this is at the core of all of our new ongoing work for large CT report generation, the next generation mammal models, et cetera, because it's critical to be able to handle this like long resolution, like very long context stuff without dropping performance. Any questions here before I move on?
How big is the token?
Yeah, so in these experiments, the tokens are functionally 16 by 16 pixels. For this paper, we have a synthetic high resolution benchmark based off ImageNet. You take ImageNet, you make it really big, because this is public data that other people who like write vision papers can compete on, unlike our mammograms.
So if the image has different resolution, then the size will be different, right?
Yeah, well, we're in these experiments, just to understand the method, we're taking images and we're making them 4K by 4K. So like the thing we're looking at is, if I go back a couple slides, where this is the minimum resolution we care about. And this thing, all the things are squashed, right? Like at the 1K regime, the speeds you can't really tell the difference. But there's where we do a bunch of experiments. But then the really thing we care about is how does the accuracy change as you go up? So this last bar plot, like these 3 bars, is showing, one more, at 1K resolution of 3% better than Mamba vision, which is the most comparable thing in speed. But as the resolution gets bigger and you have more emphasis on the long context, the performance gaps keeps growing. Does that make sense? Okay, cool. So this is one part of the picture, right? And I've already shown you some easy workflows, like you can do this immediate workflow trial thing, you can do this MRI screening thing. But really all we talked about is how do you make better predictions to model more of the world? And that is not enough, right? Because we just don't want better predictions. We want to like make real recommendations to help people. I call that control. And that's kind of that second picture in these slides, right? Like if you have a better risk model, the premise is you should be able to do better personalized screening. And one of the things that I learned when I built my first risk model is that my clinical colleagues could not tell me how to do personalized screening. And so this led to a new set of work focused on how to design the screening policies as a multi-objective RL problem. Okay, so to kind of zoom back, once again, motivating story. Some people do the same thing. By now, you might imagine people have different tissue, they have different mammograms, they have different risk profiles. So even though you tell them to do the same thing, you have very different outcomes. So the person in blue could get a later stage diagnosis. The person in green could have nothing. A person in yellow could have had unnecessary biopsy despite having nothing. And so this is kind of the ongoing dual challenge, both late detection and over-screening, and the pattern isn't the same across populations, so it's also implicated in disparities. So the holy grail for a long time has been, how do you tailor this to the individual patient need so that you would know to give the person on blue the most sensitive regime, which in practice might be like MRI interleaved with mammo, not just mammo, and the other people less screening based on their actual need. That makes sense? Now, to set the stage for this, it's like about how do we actually make guidelines today, and will the current process ever get us there? We have many different physician organizations, expert committees like the NCCN, the USPSTF, which I will struggle to pronounce, the ACR, and many others. They meet once in a while, sometimes every 2 years, sometimes every 5. They look at the literature and they say, here's a one-size-fits-all guideline. Do this biannual at age 50, or do annual at this age. This process has resulted in multiple conflicting one-size-fits-all guidelines. And I will argue that this will never be able to yield some like highly refined algorithm with changes dynamically on the fly as new technology comes out. Like it's not built for this kind of thing. And because it's just expert review, there's no like, it's a literature review. Like there's no explicit validation of how does this change care at UCLA. There's no infrastructure for that. And so I would argue this process is never going to get us there, and we want to do something different. This is my pitch, right? Where we can treat policy design itself as a learning task. Now, we're not predicting risk anymore. Like it's given the patient information. I write here risk as like the picture, but you can put anything. Here's a scale, but in the paper, we actually had all the risk scores across time. What we're predicting is an action. You get screened in 6 months, in a year, in 2 years, 3 years, etc. And the thing we're optimizing for is reward. And by that, I mean it's a weighted combination of early detection benefits, however we want to quantify it, and screening harms. Here's the cost. I'm saying like a holistic version of what you don't want to happen in screening. Okay, so intuitive idea, you want to optimize the thing as a policy problem. The key question is how, right? And the key idea of the paper is you do not need like, well, there's modeling papers that inform USPTFF, or whatever the acronym is, that inform by national guideline organizations. They tend to model everything. They simulate a hypothetical patient population, hypothetical how screening interacts with them, and then they make some decisions. I want to simulate the absolute minimum that I can. And what I'll argue what that is modeling we rather happen to a person in hindsight. So let's say we have this patient in blue, got screened in year 0, year 1, and year 2, and they got a late stage diagnosis in year 2. All I need in order to make a screening policy is to say, for a counterfactual hypothetical screen for this individual person who I know was born in real life and had cancer in real life, what would I rather happen to them in hindsight? Or another way to phrase that is, how would I have ranked this counterfactual screen with all that I know? This means defining 2 functions. One is a cost function, which is usually easier. Here in the paper, I have something very simple. It's kind of like normalized screening volume. Assuming it's kind of proportional to the risk of biopsy and stuff, you can have something fancier. And here I can say, okay, there's 4 screens in a time period instead of 3. So the cost here is a little bit higher. You can make this richer. You can define this however you want. The other thing is how do you define benefit? Once again, you can define this however you want. I had here something very simple where I'm just looking at a shifting in diagnosis date with some assumptions and a test sensitivity to that assumption. In reality, what I would want to do is like, if I know the cancer size, I can put in my favorite growth model. I can have many different definitions of reward. But if I can pick what I would, with the power of hindsight, how to have ranked a counterfactual decision for this patient, you need people who get cancer, which is very easy. People who don't get cancer, it's even easier, right? There's no benefit by definition. The cost function is the same. And I can run this across an entire retrospective population. So if I give you a policy, you can test this policy at UCLA. And you can say, well, I can change the assumptions to something I'm comfortable with. I can look at these hypothetical screens. If I can test it, it means I can also train it. That makes sense? Okay, so this is the learning framework, right? Like now we're going to simulate how we think policy should have been, which encodes our assumptions about the world, given the power of hindsight on our retrospective populations. The next question is, well, how do you learn the policy? Right? And there's the first option that I thought of, which is wrong, that's a preface, is you can do imitation learning. Right? With the power of hindsight, I can say, well, what's the perfect screening? Perfect screening is you avoid every negative screen, you get the maximum early detection one, done. Right? And you could say, let me train my model to copy the Oracle policy. That's supervised learning, imitation learning, tomato, tomato. Anyone have any intuition of like why this would not work. I didn't either. That's okay. Go ahead. It's actually not that. It's just not tractable learning goal. So the reason why it doesn't work is you're predicting the oracle action, which is not the same. It's the oracle action across all possible risk policies. If I had a perfect risk score, this would work. But I don't have the perfect risk score. So I'm going to fail somewhere that it has some distance away probabilistically from the real one, but it's not biased towards a good solution at all. You see what I mean? That you're predicting what's perfect, even though you have imperfect tools. So what you really want to do is you want to predict how well you can do from your tool, which is not, it's not the oracle policy. You see what I mean? Another way to view it's like this generally predicts either come back in 5 years or come back in 6 months. The average of that is come back in 2 years. If it can't actually tell the difference, it's not, the risk score isn't powerful enough, you're going to collapse something very bad. So instead, we can, if you view it as reinforcement learning, then it actually works. What does reinforcement learning do? It's given my states, which in this case is my risk score, what is the value of each of my actions if I roll it over time? So I'm literally predicting what's expected costs and benefits of my policy at this time if I follow it. And if I bootstrap that, I'm actually learning how I'm trying to maximize how well my policy can do with my actual risk score. And that's much better in practice. Now, everything I'm showing you here assumes you have a fixed trade-off of detection benefits. In practice, there's no way we're going to agree. I don't agree with my mom on my risk trade-offs. You know, it's the fact of life. And so at the modeling side, we actually can leave this as unknown. So at training time, what I have is I have the risk score. That's my states. I put in a preference of how I want to weigh across my multiple objectives. And at training time, I actually sweep over all possible lambdas. So that way I can give you a Pareto optimal curve of possibilities. So as a user, you just pick the threshold. And my goal here is no matter where you want to be, because like Sweden's going to have different trade-offs and we are, I mean, we might have different trade-offs than like a place in Chicago. Like there's going to be always room for disagreement because that's the value statements. So I want to support all of that within one model. People follow? Okay, so experimental setup. The models I'm about to show you are trained in MGH, the same place I built Mirai, the breast cancer risk model. I'm also doing 0 shots, no adaptation, external validation, the other sites where I had longitudinal data. Cool. Okay. The results all look of the following shape, right? On the x-axis here, I'm showing you mammogram volume per year. Further to the right is better, less frequent screening. On the y-axis, I'm showing you here my early detection metric. So up is higher. This is kind of relative month shifting compared to actual diagnosis dates. And what you see, even as you sweep the assumption of what the early detection metric is and how much early detection is possible, you get the exact same curve where by using tempo with a better risk model, let's say you want to do the benefit annual screening. You could, by allocating people screening correctly, you could have a quotaless mammograms in general. If you wanted to use, on average, annual screening, you should be able to shift the diagnosis date by 5 months in the MGH system. And you see the exact same trend in Karolinska and CGMH and everywhere else. And kind of a key benefit of this framework is that you can actually test it. Like you can actually run it on your population. You can see how it behaves. You can dislike some operating points, like some other ones, pick your threshold, and that's the basis of a trial. So to summarize, what I've been talking about here is how you can learn personal screening policies, not by modeling whole populations, but by modeling individuals. All you need to say is for this individual person, who I know how they were screened, I know what kind of cancer they had, what would rather happen to them in hindsight. And this notion is applicable with arbitrary types of reward design and arbitrary risk models. I didn't show this earlier, but like I tried this with Tarcusic. In the paper, it's an orange line. And the orange line is like fully below the blue line. Right? So the better the risk model, the better the shell of things go through, and you get better trade-offs. And if you do this well, then we can kind of like cut the Gordian knot. You have both better early detection and less overscreening. Okay, so this wraps up that paper. And we have a lot of new ongoing work in the space. But before I move on, any questions? Okay, cool. So let me tell you a little bit about ongoing work in this area. So it's one thing to say, when I have imaging, how can I make my screening program more efficient? Right? That's the thing. That's what Tempo 1 is trying to solve. But that's not the only problem in cancer. There's a bunch of questions. How do you even start screening? Like in pancreatic cancer, it's so rare that we don't know how to select the population high risk enough to make screening cost effective for them. In breast cancer, for women below 40, we do not know how to identify this population. And so I still get emails all the time from women who have metastatic cancer before 40. It's like, what could we have done for these people? And the same picture I said of like, we need to understand who's going to get it and do something about it remains the same. but the input we have is different, right? Because we don't have imaging de facto. So one thing I've been looking at, and this is joint work with Mikkel, who's in Denmark, is how can we model everything we know about the patients before imaging to predict risk of cancer? So to make the setting more explicit, this is a uniquely Danish thing, but eventually we'll do it here too. We have access to EHR records like disease codes, lab tests, etc., of the individual across a lifetime in Denmark. And we have the information of their parents. So like, I consider family history, it's not family history of cancer as a questionnaire, but the actual raw record of your parents' health trajectory over time. And given all of that, we haven't done this yet, but we also can expand this to like, what's the exposome? You can do your neighbors. You can do a much richer view of what's happening in your community. And all my task is, the rest of the model version is what's the risk of these different kinds of cancers at each year. But the action version, which is what we're working on now, is should you get screened for this cancer this year or not? And the kind of fundamental thing we're looking for, you can make the screening program more efficient, right? Because you have some information, so you can skip some of the mammograms that you're not going to have. But the primary goal is how do you help people who are currently unscreenable? The women before 40, the non-smoking people who are going to get lung cancer, people with pancreatic cancer, etc. Now, I'm interested in very early preliminary results here, but this had the same shape as what we showed you before. X-axis is screening volume. This is like average screenings per year. I'm showing you just breast cancer and lung cancer. The red line and the blue line is if you change the starting age for annual and biannual screening. And what I'm showing you here is the early results of this kind of risk-based thing, where the TLDR is like, you can get more efficient. And this holds not only in the overall population, but for people below 40, and for people who don't smoke in lung cancer setting. And while this is early times, it's going to take some more work to kind of like adapt this to the American context where we have this like very fragmented health system. It shows the same overall picture. There's so much more context.
Because I prefer these over like in my ears because my ears are too small, so they fall out.
Okay. Cool. Okay. The future of enabling risk-based screening at scale. We're never going to get there with just age. We got lucky that age is enough of a risk marker to start breast cancer. And I think that's the future of that area. And there's a lot of new method work. It's the same kind of thing. How do you scale it? Because there's so much we know about your community at the same time. Okay, so this wraps up the control picture. Any questions about this before I move on to translation? Yes.
The families over time and having all of the EHR data, but I was wondering how much, like within that health system, is there access to any like mutational screening as well, and how like rapid mutations, like these germline mutations that we know contribute to breast cancer, were integrated in that? And I know it's pretty new, kind of in the U.S. and here at UCLA with the Atlas and stuff like that. We're trying to see how we can integrate kind of this genetic data with screening as well. So if you have any experience with that.
Yeah, I mean, my experience to date says every time I try to get any non-trivial volume of genomic data, I have failed. So that's my raw answer of my experience with it. Philosophically, I try to model, what do we, like, I come from computer science worlds. AI methods is my tool to try to create change. And where am I most empowered to make a difference is where things are already large-scale volumes. I'm not using it well enough. So that's kind of biased me towards, we have so much imaging, and all we did was density. We have so much EHR data, and then we pull out age. So like that, I'm drawn to those problem areas. Is the potential in genomics? For sure. Right now has not been kind of the top of my priority key because it's so hard to access at any scale and so unavailable. There is stuff like how do you suggest people genetics testing and stuff, but we don't even know what we can do before we even change the data pipeline. So I think people should do it. I think it's really important. This is not my particular impact pathway right now.
Yeah. Population of raw records from like parents and other families, so that doesn't include genetic data, right?
Does not include genetic data. Yeah, I mean, I guess it does so in a proxy that you have family history stuff, but it's not like directly, there's no genomes there. Yeah, I'm actually looking to start a version of this project across the UC system because we have, the UCY DID data cohort. I think there is big opportunities there. Challenges are that cohort is not linked to the state registry and it's not linked to notes, so I can't even do LLM stuff on it. There's like some trickiness to get it, but if people are interested, I think this is a big opportunity, and it's something that it's going to be hard. But like best hypothesis is like how can we make pancreatic screening possible? That's my best hypothesis. And I think there's a huge amount of health value to be created. Okay, if no more questions, we can move on to the last chapter. This one's shorter. So the last bucket, let's say you have predictors. Cool, better predictors means you can do some things. Let's say you have control. Well, I can do more things, right? And this can adapt to the predictors on the fly. Very good. That's not enough, right? Because that still lives in paper land. Like we want to actually translate things out to help real people. And that is a broad problem with translation. And to recap, I already mentioned there's 2 ongoing trials with MIRI-1, right? There's this MRI thing, there's the same-day assessment thing, and yet it's already obsolete. And this is a central problem because we already have a better model. And vanilla, your trial results for model 1 do not say anything about model 2. And what that does is it creates disincentive to run trials. And it means that the community often waits, like, when do we think we have peaked? And then we're going to spend the money to run the trial. And that's just bad because if we're doing well as an AI community, we should actually not, we should be expecting numbers to get better over and over again for years to come. So this is kind of the key question that we've been looking at for a little while now, because we saw this obsolescence coming. And so Wenxing Zhang at Berkeley, who's a bioscience student, has been leading this work. And we were looking at how can we come up with a new kind of trial framework that effectively uses the special properties of the AI models. Okay, so what is that special property? The special property, which is often true in every trial where we're doing allocations of screening, allocations of treatment, is that the AI model itself is not the intervention. Like MIRI does not do early detection. The MRI might catch the cancer early. And what MIRI would do is help you get an MRI, right? Like if you're trying to do treatment response work, and trying to say this person will benefit from the adjuvant therapy, the person is not responding to the model, they're responding to the therapy that the model selected. And there's a huge class of problems of this shape. There's a very special causal structure where the actual intervention that you're studying is something else. And all the AI model does is it allocates that intervention. And when you do that, if this AI model gave you the intervention, or the next one does, or the previous one does, it does not make a difference, right? This is property we call exchangeability. And if you can make that assumption, then you can now do adaptive trials, where let's say I run, to give a motivating example, I finished the MIRI-1 trial, right? In the SDA setting, it's going to require 100 patients. And now I want to get a rigorous, valid causal estimate of what my number will be for MIRI 1.5. Well, I can run both models in hindsight. It's like that's very cheap. And like former drug trials, I can actually see the eligibility criteria very easily. And I know that 70% of the patients high risk by MIRI 1.5 were also risk by MIRI 1. That makes sense? I can look at overlap because if one model gave you the recommendation or the other, it does not make a difference in your actual outcome. And now all I need to do in this adaptive trial is now I need to turn on data reuse. I need to enroll the 30 patients of the kind that are new, that are not in the prior versions of the trials. And as you run more trials, it actually gets cheaper because the odds that you're in the overlap of prior models gets bigger. And we can show this, like MIRI is not my first breast cancer risk model. I had another one before then. And so if I look at the union of that model and the MIRI 1.5 model, next trial only requires 5 patients. And so the whole point of this work is it's, showing the actual skill assumptions you need to make this true, the new sample size calculation formulas, how you implement the enrolling strategy, what happens when you only have changeability within subsets. Let's say MIRI only, the 70% were all young, but now you have the people are older. So like, how do you incorporate that? But the basic idea, and the thing I want to really get across is that because these things are not interventions, they're just allocation functions, the overlap gives us a lot of statistical flexibility to change the way we think about evidence so that it actually gets cheaper over time and not you're starting from scratch and you have all these bad incentives. Any questions about that? Yes.
Which patients were specifically stratified as high risk for the previous model?
Yeah, you're looking at like, which patients that have already enrolled and have already gotten the intervention would have been enrolled if I had my model a year ago. Because for them, it's not like the model that gave them the MRI changes the outcome. Like that's a very reasonable assumption. So if you can make that assumption, you can now enable data recycling. Now, the rest of the question is like, well, how do you make that rigorous, right? What if that was a subset of the population? That subset of the population is a different effect than the other subsets. Now you have stratified exchangeability, and then you can do a bit more stuff. But the basic idea is that like in a simple setting, if you already enrolled 70 patients, oftentimes you're able to reuse all 70. And now your trials are getting small as you go along. And what that leads to is a framework in which we view AI evidence not as a single snapshot like we do for drugs, because they don't change. You just have them as platform trials that are just getting cheaper over time. You can have this kind of rigorous continuous evidence thing going on. And I view that as a feature of the space. It just, money is always the problem. Yeah. Okay. So to recap, this kind of finishes the prior papers and ongoing work section of the talk. I think that to make this kind of future of AI-driven care possible, we need key innovations across the kind of 3 core buckets. One that looks very CSE is how do we actual model the gigabytes of information that we have per person to understand the outcomes we care about, like cancer risk, treatment response, which diagnostic things, and that itself has some immediate low-hanging fruit to make care better. To take that to its full potential, there's so many key innovations we can do in the lens of control, because making guidelines is hard. That in itself can be fundamentally an AI problem in which you can adapt to test on preferences on the fly. And that's something between reinforcement learning and causal inference. And finally, even as we have these things, we should expect they do better. And there's a lot of room for key innovations in how we rethink our evidence generation frameworks to have a evidence framework that is compatible with the expectations of fast innovation. I just want to close with, okay, what if it all works? You know, what if these 3 pieces come together? We have a bunch of things that are useful in practice. I think we have a massive opportunity to rethink how we do our screening criteria to make them more effective, reduce the total advance rate of cancer, which has its own costs, but also reduce the volume of screening. Both in places where we have screening, but also where it's not currently possible, like pancreatic cancer. So I think there's a huge clinical difference to be made here. With that, I want to thank you all for your time and take my time for discussion and questions.